Hi, welcome to Elasticity. This is our last topic, which is how do you do approximate solutions for elastic problems. Excuse me. So we saw that for exact solutions, when we did exact solutions, either it was trivial or impossible, right? Because of stringent requirements. So what can we do? So we have several strategies: purely ad hoc, which is a strength of materials approach; requires lots of intuition. So if you look at this one and you're thinking, generally speaking, when people hear ad hoc and intuition and all of that, they think it's bad. No, this is very good. Will give us jobs. You know what I mean? Right? So if there is no intuition required, everything is a procedure, then there is no need for you. So of course companies want to have situations in which there is no intuition required, nothing is ad hoc, everything is clear. So that's one extreme. So what happens is that's one possibility. The second thing is partially ad hoc. And this is the Saint-Venant type ideas. And this still gives us PDEs to solve. Okay. Then the next one is fully numerical. The problem with a fully numerical scheme, and there are two things you can do: finite difference, finite element, etc. So right now we have the hegemony of the finite element scheme to the extent that people actually think that mechanics means finite element. That's actually not true. Okay, finite elements is a small area of mechanics which has some practical use for finding fully numerical solutions. So it has some very good advantages. Don't need to think. Okay, well, it's not really true, but I'm just telling you. Okay, so what it means is that you are replaceable. And you're hoping that by that you will get promoted. You know what I mean? If you're irreplaceable, you will not be promoted. So it's a bad thing. So my point is, okay, fine. You know what? If you do a fully finite element method, you think it's magic. You press a button, you get some color pictures, and answers are all fine, everything. But you cannot do parametric studies. So it takes too long. And what happens is, the answer from many people is to just say, buy a big enough computer. I mean, that's a waste of resources. And that's again one of those things which at a high level, you have to ask yourself, do you really need it? It's like saying, in order to kill a fly, what I need is a flamethrower. Yes, it will kill a fly, but it will kill also everything else around it. So, you gotta match your tool for the task. Okay, so that's a crazy thing to do. But that's what we are doing right now. So please remember that these kinds of things are fully numerical schemes. Now, there are a whole bunch of things which are called semi-numerical. Or semi-analytical. This uses symbolic manipulation plus numerics This is somewhat new because symbolic manipulators have just, like Mathematica, Maple and other things are still being used primarily as small tools in engineering classrooms. We have to use it much larger, and I will show you that symbolic manipulators are very good for doing certain things. But you cannot do everything. It cannot give you exact solutions for everything. People do entirely symbolic or entirely numerical. I am thinking you can do something together. Okay, so there's already one method that does that. These are called, which are called boundary element methods. Or Green's function methods. And they work by doing exact solution for point load, and then approximating. So this is one what I am going to talk about, and this the second method, which is again very popular, is called the Ritz method. And this is actually very popular in the vibrations community. And this works for both linear and nonlinear problems. This is quite good. The thing is, requires judgment. And by the way, this method predates finite elements, all of these things. This is a very old method. Many times it's called the Rayleigh Ritz method. And I'm going to show you how to use that, just to introduce you to it, so that you realize, no, not everything needs this. Don't blindly go to this kind of thing. Use your brain so that you can earn your keep. Otherwise what happens is, after a short time, they will say, why are we hiring you? So how does this Ritz method work? So for elastostatics, how does it work? Step 1. We know that, before I do step 1, let me back up a little bit. I want to do something slightly different. Idea is that the solution to elastostatics will minimize the strain energy. Among all KADs. Remember what's a KAD? Kinematically admissible displacements, right? So what does it mean? Find UI that minimizes integral Cij KL epsilon ij epsilon KL 1/2 over the whole body minus integral over the partial omega traction, only traction boundary conditions, T dotted with UdA. Remember this, right? So this was the energy, and find things that minimize this. That's the idea. So what we do is approximate solutions will do approximate minimum. What do I mean by approximate minimum? We are not going to minimize over all possible KDs only over a parameterized subset. That's it. What do I mean by this? So I'm going to talk about the general procedure, then we'll look at a particular example. Okay, general procedure. So we are going to do 2D isotropic elasticity. The idea is the following, right? U of x comma y equals summation ui fi of x. These are known functions. Sorry. Fi of x comma y. Right? So these are known functions. V of x comma y equal to summation vi fi, let's say gi of x comma y. Again, these are known functions. These are unknown constants. Right? So I equal to 1 to n, j equal to 1 to n. So how many unknown constants? Total of 2n unknown constants. So our task is find the 2n constants such that the energy is minimized. So we have to make sure that it has to be KAD. So you cannot pick anything you want. You cannot pick the FIs to be anything you want. It has to be kinematically admissible displacement. Otherwise it will not work. Okay. So it has to be kinematically admissible displacement. So rather than looking at all possible things, we are going to look at only some possible kinematically admissible displacements. These are usually called shape functions. Okay, so these are known a priori, and there is nothing which says you have to pick polynomials or anything. Pick whatever you like, which you think is reasonable. So judgment is involved. Okay, so how do we do this? I'm going to show by example. So this is how we do. I have a cantilever B. And then I have a force distribution that is cubic. And I want to find out the displacement. This is, so okay, y equal to plus or minus h, that's what it is. Okay, and then x equal to 0, x equal to L. Okay, so what it is that I don't want to do this, I want to be able to do this symbolically, and you know this is a square cross section. I can do by area function. We know how to do that, but I don't want to do that. I want to show you how to do approximation. So what you do is you say, okay, fine, I'm going to assume u of x comma y equals axy. You're wondering, well, how did I know that? Because this means epsilon xx is a times y. Can you see that? And I am assuming that the strains are linear. Okay. V of x comma y equal to a naught of x plus a1 x squared plus a2 x cubed. Sorry, we'll call this a3, a1, a2. Okay. So notice this. Why did I assume this? Because roughly speaking, if I have a cantilever beam, I will get a cubic dependence. PL cubed over 3ei is deflection, and also I am assuming no variation in the y deflection through the thickness. You know, you can do, I mean, this is where if you say, oh my goodness, how am I going to do it? Well, this is what you get paid for, my friends. The ability to come up with ideas, pictures for these things. Okay, so this is a good assumption based on cantilever beams. You can do something else. I mean, there's nothing, for example, you can do, okay, fine, I don't know what to do. I'll put an x to the n and put n equal to 1 to 7 or 1 to 5 or whatever you want. I'll tell you a little bit later how to pick something a little bit better than this. Okay, right now, so what it is that find these four constants. So instead of, so problem reduces to instead of finding u of x comma y and v of x comma y, we just need to find a naught. So a, a1, a2, a3. These four constants. Okay, and I'm going to make my life a little bit easier also. So that's step one. So this is my assumption. This is the f of x comma y. These three things are the g of x comma y, the shape functions. Okay, roughly speaking, the shape is determined by those functions. So if you pick different shapes, I'll get different possible shapes for the beam. That's how it works. And there are only four constants. Okay, now what I want to do is to say, okay, given these four constants, let us calculate the string. Epsilon 1 is du dx, which turns out to be a times y. Epsilon 2 equal to dv dy, which turns out to be 0, right? Because there is no function of y. Epsilon 1 equal to 1 half du dx plus dv dy. Sorry, du dy plus dv dx. So let's do it that way. And then this turns out to be 1 half du dy. Du dy is ax, and then dv dx will give me my plus a1 plus a2x plus a3x squared, right? So I want to think, okay, I'm going to look at it, and I know something about the fact that shear stress is parabolic. This is again strength of materials type of stuff. So I want to get rid of the x term. You don't have to do it, but I'm just, because I don't want to do a lot of calculation, but what I'm trying to tell you is, the more insight you have about stress distributions, the better you will get at picking the functions and simplifying your life. In this particular case, I'm going to say, okay, fine, a plus a2 times x term, I want it to be 0, so that it's only parabolic. You can see a1 and a3x squared. Just, I mean, let's not take it too seriously, you know what I mean? This is a crude idea. So what happens is I will get a2 equal to minus a1. So I got rid of at least one of the constants. So I got a2, a3. Okay. So what I'm going to do is Next, I want to calculate the strain energy. U equals integral, if you remember, it's lambda. So 1/2 lambda epsilon II epsilon kk plus 2 mu epsilon ij epsilon ij dx dy. So this is double integral, goes from minus h to h, 0 to L, minus integral boundary. So remember, let's go here, that's only this. So f of x there is x cubed, so I'm going to put minus x cubed, and then v of xy, v of x comma 0 dx. So y is h. Okay, now you have to do this, and this is a pain. Okay, even this, see, starting with this is okay, even calculating these things are a pain, and then it starts really getting painful here. This is where this integral, if you do simple enough functions, you can actually do using Mathematica or something, which is what I am going to do. I am going to show you what it will look like if I use Mathematica for this. Okay, let's see. Okay, so I'm going to shrink it so that both of them can fit. Okay, so I'm going to shrink it here. I'm going to show you the Mathematica side of it. Okay, first thing I do is I have u and v. U is a times xy, v is a1x minus a2 over 2x squared. I mean a, because a2 was minus a, so it is minus a over 2x squared plus a3 over 3x cubed. So the constants are this, this, and this. So there are only 3 unknowns. I have to get 3 equations. So we'll see how it goes. So I'm going to say shift enter. So now I have plugged in u and v. Now look, strain epsilon 11 is du dx, epsilon 22 is dv dy, epsilon 12 is 1/2 du dy plus dv dx. Okay, and the energy is 1/2 lambda times epsilon 11 plus epsilon kk squared, that is this term, epsilon ii epsilon kk plus 2 mu times epsilon 11 squared plus epsilon 22 squared plus epsilon 12 squared. Sorry, there should be a 2 here because there are both epsilon 11 and epsilon 22. Okay, so let's see what we'll get. Right? If you do that, you get this. So let's go up here and stick it here. Let's see what we'll get. There you go. Can you see that? 1/2 a squared lambda y to the half. Let's write it down so that we can see this. So what did I get for u? This part I got let's see, where is my okay, 1/2 a squared lambda y squared plus 2 mu 1/2 a1 plus a3 x squared plus a squared y squared. Okay, so now what I want to do is integrate this thing. There, left hand side is integrate the energy from x equal to 0 to L and y equal to minus h to h. So I am doing this thing. Okay, so off we go. I'm going to go up here and I'm going to say There you go. I got a messy thing, but that's okay. Okay, so I'm going to write this. Let's see. 1 over 15 HL times 15 A1 squared plus 10 A1 A3 L squared plus 3 A3 squared L fourth. I'm just writing it down. You don't have to do it. I'm just showing you what you will get. Okay. That whole thing times mu plus 5 A squared H squared times lambda plus 2 mu. That's the energy. This thing, U. And I'm calling it the LHS because I'm going to soon show you what happens. Now, there, f of x is x cubed, RHS is this guy. Okay, the right hand side, the reason is because that's the load function, right? So I'm going to show you that thing. So the load function, external load, integral f of x v of x comma h dx 0 to L. So how do I do v of x comma h? So there is the f of x, that thing. There is the v of x comma h. So I have said take v, substitute v y equal to h, and then integrate it from 0 to L. So if I do that, I will get there. So this whole thing turns out to be A1 L to the 5 over 5 minus A L to the 6 over 12 plus A3 L to the 7 over 21. So what is my energy now? Total energy U, which is a function of A1, A2, sorry, there is no A2, A and A3. These are the three things, right? Equals all this junk 1 over 15 HL times all this junk minus all this junk A1 L to the 5 over 5 minus A L to the 6 over 6 plus A3 L to the 7 over 7 over 21. Notice, instead of being a function of ux and uy, it's now a function of just three variables. Now I want to say find A1, A2, A3, sorry, A1, A, A3 that minimizes u. How do I do that? I do partial u with respect to A1 equal to 0, which means this. So let's go up here and I want to say there are two pieces. I have to do this and that. I am going to do both of them. A1, A1. There, it tells me, of course I could have done that by hand, no? But I'm just going to show you. This tells me that let's see, 2 over 5 h times L 3a1 plus a3l squared must minus L5 over 5 must be equal to 0, because that's my condition, right? So that will give me one equation for a1, a2, a3. What's the other one? Let's try it for d side du dA equal to 0. You can go up there and you can go up here and I can put A. And I'll repeat this thing. Now this gives me, let's see, what does it give me? 2 over 3 AH cubed L times lambda plus 2 mu equals minus L to the 6 over 12. Hey, that's nice. I got A equals, I can get rid of this 4 and then I can get rid of this L, that is 5, and you know, we can do all this simplification and I will get minus L to the 5 over 8AH cubed times lambda plus 2 mu. Right? And then the last equation will be the one in which I put A3 here. Differentiate this with respect to A3 and you will get one more equation. 2 over 15 HL times 5A1 L squared plus 3A3 L fourth times mu equals L to the 7 over 21. This is the last du dA3. That's it. So you solve this and you'll get A1, A2, A3 in terms of these variables. This will be an approximate solution. How good is this approximation? How good is it? It is as good as original assumption about shape functions. What do I mean? Everything depends upon this. That if you get, so if this is a reasonable approximation and you have enough flexible parameters, you will get a good solution. By the way, it will always overestimate the stress. The actual beam will be more flexible than this, because in this case the assumptions always restrict flexibility. What do I mean by that? So if you go back to our idea, okay, the original statement, so we are done with this, so let's go back here. Okay, the original actual minimization problem is this. The actual minimization, come on. The actual minimization problem is among all kinematically admissible displacements. So it allows the beam to be very flexible as long as it meets the boundary. But our solution here was much more restricted than that, because we allowed only for certain kinds of deformations. So it will always be more flexible, I mean, the actual beam will always be more flexible. So the stresses that we get will always be higher. So this always gives you upper bound for stresses. It gives us upper bound for stresses. That's what happens. Okay, but I got the method, right? So the method consists of assuming, so let's go back and make sure. The method consists of assuming some nice forms for u and v in 2D and u, v and w in 3D. What form you assume is based on your intuition. So this is where your intuition plays a role. Calculating the strains, calculating the displacements, integrating the strains out, and calculating this, carrying out this integral, and then differentiating. The result will always be a function of the parameters a1, a2, a3, whatever. Differentiate it with respect to the parameters, set it equal to 0 because that's the minimum condition, and you will find algebraic equations. The thing is, there are two steps where you might have to do approximation. First step is here. You may have to do this integral numerically. When you do that, you will lose the parameterization problems, but you will have to try and see how much of it do you really need numerical, how much of it can you do analytical. So don't just blindly do numerical integration. Sometimes you may have to do numerical integration only along the y direction and not along the x. That's okay, so that you can get this one. The second one is solving these algebraic equations. That's actually not a hard problem. In fact, in many cases, you don't even have to solve the algebraic equation. You can go right up here and use a minimization technique. There are a number of these things which allows you to find the minimum of functions. That's the other way to go. Right? So this is a different idea. You don't even have to do the differentiation. So, and it can be entirely automated. Everything depends upon your shape functions. Finite element methods also do the same thing, except that they pick lots and lots and lots of shape functions irrespective of the problem. Okay, so that's the idea. Thank you.